All right, guys, are there any questions over any of the assignments thus far? Questions over any of the assignments thus far? So, what we're doing today is inverse matrices and systems. Inverse matrices and systems of equations. Now, to take the inverse matrix of a 2 by 2, well, to take the inverse of any matrix, it does need to, first off, be square. We have to have a square matrix to find its inverse. Now, the identity matrix for multiplication, I, is a square matrix with 1 for every diagonal. So we call a matrix the identity matrix if the diagonal is all 1s and everything else is 0s. Square matrix, diagonal of 1s. Everything else is 0. Because whenever we use the dot, 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 that just means everything in between it is the same. So any matrix square, so 2 by 2, identity matrix would be this right here. If it was a 3 by 3, well, and no matter how big we make it, the diagonal of 1s going from left to right is going to be 1. Doesn't matter what else it is. Because if it's a diagonal of 2s, it's not the identity. It has to be a diagonal of 1s, and everything else is 0s. It's called the identity matrix. From left to right, it has to be this way here. It has to be this way here. And the reason that this is nice is that we have this identity matrix is the identity matrix is the same as the multiplication of 1. Because a times 1 is still a. It's our identity multiplication. It gives us back what we start. Because if, as it says here, we multiply matrix A by the identity, or we multiply the identity by matrix A, we still get matrix A back. It doesn't change the matrix. It doesn't change what it is. And as we've seen already, left and right multiplication with matrices is different. So the only one that it's not is if we're multiplying it by the identity. Now, also with that being said, if two matrices are inverses of each other, when we multiply here, matrix A by its inverse, we will get the identity matrix. For two matrices to be inverses, their multiplication has to give us the identity. And really, it works in either way. So for A and B here to be inverses of each other, A times B and B times A should both give us the identity. A times B and B times A should give us the identity matrix. And realistically, if one of them doesn't work, if A times B doesn't give us the identity matrix, it doesn't matter what B times A is. So we're wanting to see, is A and B, are they inverses of each other? And to figure that out, all we need to do is take A and multiply it by B. If we multiply these together and get the identity, you can put it in my chair, we get the identity matrix, which for a 2 by 2 is this here. If we get the identity matrix, then they are inverses. If we get something other than the identity matrix, then they are not. Now, there's two different ways we can do this. One, we can do this by hand, or the other is in the calculator. Either way. Because if we remember this last week by hand, we go over and down. Negative 4 times 1/4 plus 2 times 1/2. we go over and down again. So negative 4 times negative 1/2. So negative 4 times 1/2, and then 2 times negative 1. Then we do this again if we're doing it by hand, so over, down. So negative 2 times 1/4 plus 1 times 1/2. And lastly, over and down, we would have negative 2 times negative 1/2 plus 1 times negative 1. Now at this point here, we would need to simplify this. And most likely, if you already typed it in the calculator, you already have the answer. Negative 4 times 1/4 is going to be negative 1. Plus 2 times 1/2 is 1. Negative 4 times negative 1/2 is going to be 2. Minus 2. Negative 2 times 1/4 is going to be negative 1/2. Plus 1/2. Negative 2 times negative 1/2 is 1. Minus 1. Which gives us the 0 matrix. So is the 0 matrix the identity matrix? So these are not. So they're not inverses. Because we need the diagonal of 1. So we need the identity matrix. Incidentally enough, if you're able to multiply a matrix by the 0 matrix, you'll get a 0 matrix. Because anything times 0 is 0. Questions on this here so far? I'm going to grab a note sheet for myself so I can read this a little better. So here we want to determine whether f and g are inverses. This time I will work it through. We can do it together in the calculator. So in the calculator, the first thing we'll need to do is put the first matrix in. So we can go second matrix, over to edit, and we want a 2 by 2. So the first one is 3, negative 5, negative 2, and 6. Now we can go for the next one, second matrix, over to edit, and down to matrix B, and it's going to be a 2 by 2. Now we can do alpha y equals enter and do the fractions, and for the most part it'll let you type them in. But I believe for the most part it turns them right back into a decimal. So for the first one, we could say alpha y equals enter 3 over 4. Enter, okay. I don't know if it left it as a fraction or if it turned it into 0.75 on y'all's screen, because I know on some it kind of switches between the two. For the next one, we can go alpha y equals enter 5 over 8. And the next one, alpha y equals enter 1/4. And lastly, alpha y equals enter 3 over 8. So we get this here, second quit. Now we just need to do the multiplication. A, second matrix, B, and we get the identity matrix. We can also do A or B times A, and we still get the identity matrix. Because two inverses, no matter how we multiply them together, if they are indeed inverses, we'll get back to the identity. So this is, yes. Questions on this here?
Nope.
We feel comfortable finding the identity?
Yep.
Well, not finding the identity, determining if two matrices are inverses. Okay. The inverse of matrix A. Now we're actually going to find the inverse. Now, luckily, finding the inverse of a 2 by 2 matrix is quite easy. Finding the inverse of a 2 by 2 matrix is quite easy. Okay, well, that's trash. Try again. A inverse is equal to 1 over AD minus BC times the matrix D, negative B, negative C, A. Now, this theorem here that they gave us is how we can find the identity, not the identity, the inverse, where AD minus BC is different from 0. Well, if AD minus BC is 0, we're dividing by 0, so it doesn't work. Now, AD minus BC should look familiar. It's the determinant. Because AD minus BC is our determinant. So if the determinant of the matrix is 0, what that means for us is that the matrix is not invertible. It doesn't have an inverse. Because if it has an inverse, we consider it to be invertible. We can invert the function. It can have an inverse. But if the determinant is 0, it does not have an inverse. So, using that here, we can find the inverse of matrix P by using this formula. So the first thing we have is 1 over the determinant of matrix P. So that would be 7 times negative 1 plus 2 times negative 5. That's just our determinant. Questions on this so far? Okay. Now the matrix itself does change a little bit. I'm going to go back and look at the formula here. So our starting matrix was A, B, C, D. Yes? In the formula, what we do is we change A and D. A and D's numbers flip. A and D's numbers flip. B and C change signs. So A and D's numbers flip. B and C's change signs. So that means for us, 7 and negative 1 switch places. So it means our top left number is negative 1. Our bottom right number is 7. They flip. The other two numbers change signs. So since the negative 5 in the top, or the number in the top right is negative 5, it's now going to become positive 5. The number in the bottom left was positive 2, so it's now we just need to simplify. For the determinant, well, 1 times negative 7 times negative 1 is negative 7. 2 times negative 5 is negative 10. Negative 1, 5, negative 2, 7. Negative 7 minus 10 is going to be negative 1/17. Well, negative 17, and it gives us negative 1/17 as a total number. Now we just need to multiply each one of these by negative 1/17, and we're done. Negative 1 times negative 1/17 is positive 1/17. One of the nice things with 1/17, as much as we can say this, 17 is prime, yes? So it means any number we have on top will not simplify with it, so the fractions are just going to stay as they are. So if we do negative 1/17 times 5, it's going to be negative 5/17. Negative 1/17 times negative 2 is going to be 2/17. And negative 1/17 times 7 is going to be negative 7/17. And this here is going to be P inverse. That's it. So p to the negative 1 for this here, we call it p inverse because we know it's the inverse of the function. Questions on this here? All right. Let's do this next one here. So to find the inverse of Q, 1 over the determinant times our matrix. So the determinant would be negative 8 times 9 minus negative 6 times 12. Inside the matrix, we would switch the 9 and negative 8 and change the other two signs. So this negative 6 would become positive 6, and the positive 12 would become negative 12. So we can simplify the determinant. We could do this in parts, or we can just plug the whole thing in the calculator. Negative 9, or negative 8 times 9 is negative 72 minus 6 times, negative 6 times 12 is, I believe, also negative 72, yes? Yes, so indeed, this would be plus. Well, wait a minute. Doesn't exist. Because we can't divide by 0. Because 1 divided by 0 does not exist. It is not possible. So what that's telling us is that this matrix here, even though it is a square matrix, does not have an inverse. There's no way we can get it or have it be an inverse. It's not invertible. Let's look at one more. We can look at 2a. And as I have a feeling, you're probably wondering how to type this in a calculator, and you can. First thing we'll need to do is pull up matrix A, 2 by 2, and we'll type it in. So for this one here, 3, 7, 1, negative 4. So we'll put the matrix in. We can go second quick. Second matrix. Okay. So I call up the matrix. I want to find the inverse, the one that I plugged in. And I'm going to hit the button we've been using for matrix, that x to the negative 1. And it's luckily for us, they've computer or plugged in and programmed these calculators to know that this is not saying that it's x to the negative 1, that we could put it from the numerator to denominators, wanting us to find the inverse. And we get these lovely numbers here. But we do have a way to turn it back into a fraction, yes? Math, enter, enter. Math, enter, enter. We'll turn it back into fractions. So this here is the inverse of this matrix. So that means even if we had a 3 by 3 matrix, we can use this here to find its inverse. There's 3 by 3, 4 by 4s. They have inverses. Unfortunately, to my knowledge, I haven't taken the time to look it up, but there's not a nice, easy formula that the 2 by 2 has to find the inverse of a 3 by 3. We actually have to use row operations and manipulations to actually get it. and it's a long and lengthy process. Any questions on this so far? The last thing we're looking at is solving equations using inverses. And what we do with this here is we take the matrices, or take the system and set it up as a matrix multiplication. Because we know we go over and down. So I can take the coefficients and multiply it by the 2-by-1 matrix of xy. Because when we multiply two matrices together, we go over and down. So if we multiply this here, 1, 2, xy, we would actually get back to x plus 2y. Same for the second row. Then we have it equal to b. And what this works out is really we're saying that a, x is our xy, is this here. Well, because this is our xy, this is our coefficients, and this is what it's equal to. As we've seen already, whenever we multiply an inverse, a matrix by its inverse, we get the identity. Just essentially a matrix of ones, which would leave our xy by itself, and the multiplication of the inverse and what this matrix equals will give us our answer. So, when we look at this here, solving this using system of matrices, what we're saying that we have is really three matrices. The middle one is going to be xy. If we had three variables, it would be x, y, z. The first matrix is just going to be the coefficients. So we have -7, 2, 6, 6. And the last one we have is 18, 0. For our case in point, I'm going to call our first matrix the 2-by-2 matrix A, and we'll call what the matrix that this is equal to matrix B. So what we're saying is I'm taking matrix A times the matrix xy is equal to matrix B. And unfortunately, we don't have a division for matrices, but if I multiply matrix A by its inverse, this here, for less of a better term, becomes the identity, becomes 1, which will leave us with the matrix xy. And what I do to one side, I have to do to the other. And more specifically with matrices, since I used a left-hand multiplication, I multiplied it on the left, I have to multiply the other equation on the left as well. It has to be on the same side, because as we've seen already, with multiplication of matrices, the order in which we do it does matter. So, this here would be our solution. And if we did this by hand, the first thing we would need to do is actually find the inverse of matrix A, and then multiply with matrix B. But thanks to technology, the calculator can do this for us. So the first thing I'm going to need to do is put in matrix A. It is a 2-by-2, and our matrix is -7, 2, 6, 6. And once we get the first one plugged in, we can go second matrix. Now we need matrix B. But matrix B is not a 2-by-2, it's a 2-by-1. And it's going to be 18, 0. Once we have both of those plugged in, we can go second quit. Now we don't want just matrix A times B, we need matrix A inverse. We need the A inverse of A, yes? So we can still start off by going second matrix A. Then how did we get the inverse? Because we just hit the -1, x to the -1, yes? Because that's how we did on the last one. So what that's telling the calculator is I want you to find the inverse of A. And we could do that and then try to plug it back in. But that's already found in the inverse, yes? Then what are we wanting to do too? We want it to multiply it by. So I can say matrix A inverse, so A inverse times B. You can put the multiplication symbol between them if you want. You don't have to. It's understood, the calculator understands that two matrices next to each other are being multiplied. It is not incorrect to put the multiplication. If you want to make sure that it does it correctly, you can do that. You can put both of them in parentheses if you want. It gives us this here, negative 2, 2. So our solution is the point, negative 2, 2. And that's it. And that's all we have to do. And again, like I said last week, Cramer's rule is not the easiest way to solve these. It does work. It is a lot easier in the calculator. It's still, I think it's kind of amazing that Cramer's rule works the way it does. As bizarre as that seems, it works, which is quite interesting. But we do have other ways that work nicer. Using inverses does work a little bit nicer than Cramer's rule, but still RREF is still the easiest way to do these. But this is the solution. I did not. Well, thank you. Any other questions on this here? Because that's the end of 4-6.